applying the idea that electrons have the same charge, so they will repel each other, and they'll find an arrangement that will minimize that. So that's the kind of the big idea. We're going to just talk about the VSEPR theory. It's sometimes called VESPR, and that stands for valence shell electron pair repulsion. So it's the idea that you've got valence electrons pushing each other away. Not all of those repulsions are equal. So the theory tells us that pairs of electrons will arrange themselves to minimize electron repulsion. Just a quick side note, I didn't give you any notes on this, but you could copy this into your document that's on the module of the assignment for today, and then that will be like a really good set of notes. So here's the idea. Lone pair and lone pair will have the most repulsion. Then we're going decreasing repulsion this way. So we've got lone pair and bonded pair is the next. So this repulsion would be less. And then the least amount of repulsion would be bonded pair and bonded pair. So on paper, this is, kind of the idea that explains the arrangement of these electron pairs around a central atom in a molecule, but we're going to put it into practice. But this is the big idea that's going to drive what I talk about next. So VSEPR theory or VESPR theory, electron repulsions aren't equal. These are the three main ones, and this is the biggest, and then it kind of goes down this way. And the idea of what drives this is kind of how close the lone pairs would be to a central atom compared to a bonded pair, which would be kind of in the middle of two different atoms. All right. So the document that you're going to work on today is this. Mine's filled out, but let's kind of walk through it together. And I've made some models that are hopefully going to help kind of demonstrate these things. So if we look at this carbon tetrachloride molecule here, we've got 4 bonded pairs. So the way that you fill this out is to fill out how many bonded pairs are around the central atom, and you count the lines, right? There's no lone pairs on carbon, so that's 0. This column is our electron arrangement, but another way to think about it, a better way, is really density. Like where are the big areas where electrons are? And we're not really interested in the lone pairs on the outer atom right now. We're really just interested in the valence shell. So remember VESPR, valence shell electron pairs, we're looking at the central atom. So the way that this would be arranged would be tetrahedral. So a tetrahedral looks like this. It's kind of like a tripod arrangement with one sticking straight up. So if all these bonds are equal, then the angles between them will all be the same. And then to get the maximum angle possible, that would be a tetrahedral. You might think it might be 90 degrees, but it can actually do better by kind of spreading out more this way and forming this tetrahedral shape, or like a tripod shape. So you'll need to know the bond angle, which is here, 109.5 degrees. So that's kind of the angle between each one of these, and it's identical as you rotate it, right? And then the shape is tetrahedral. So 4 bonded pairs, 0 lone pairs is tetrahedral. Carbon makes this very often. These could all be hydrogens in methane. They could all be fluorines, for example, and they'd all have that same shape. So next, and also, really quick, silicon would do something similar, right? So the elements in the same group do common things. So carbon and silicon would both have that kind of arrangement. Similarly with group 5, which is the nitrogen group, so nitrogen, phosphorus, and then arsenic, which is As. The central atom, which is arsenic, has 3 bonded pairs, 1 lone pair. That adds up to 4. So there's 4 areas around the central atom that have more electron density. And so because of this VSEPR theory or VSEPR theory, the lone pair that's on arsenic, or it could easily be nitrogen or phosphorus, it's going to push down more than the tetrahedral would. So we've got slightly smaller angle because the repulsion between the lone pair that's here and the bonded pair that's here is more compared to bonded pair. So this angle is these angles are able to spread out a little bit more. This one's being pushed unevenly by the lone pair and the bonded pair repulsion that exists all the way around here. So it's not quite a tetrahedral. The bond angle is a little bit lower here, and then we call that trigonal because there's 3, and pyramidal because it's like a pyramid shape. So it's hard to see. Easy when you make them, but the nitrogen doesn't sit all in the same plane as the hydrogen, so it's kind of sticking up a little bit like a pyramid. All right, so we're on to group 6 type elements next. Oxygen, sulfur, selenium right here. I don't have all of these different elements in my model kit, so we can just represent anything that's in group 6 with a red, right? And that's got the 2 bonds coming off it. There's 2 lone pairs, 2 bonded pairs, that adds up to 4. So 4 spaces around the atom. And that is because of this. These push more. The lone pairs push more than the bonded pairs, or the bonded pairs and lone pairs do. So there's kind of a lone pair coming off this oxygen right here. They push more on each other. They repel each other more. That increases the the repulsion between lone pair and bonded pair. Or it doesn't increase the repulsion, sorry, it really pushes these 2 atoms, these hydrogen atoms, closer together. So this is kind of a good example of the repulsion thing I mentioned earlier. So lone pair and lone pair is the strongest. That's going to give you more space for the lone pairs to exist, but it's also going to decrease the angle between these 2 atoms here. Lone pair, bonded pair. So this is kind of the minimal repulsion here. So that's bonded pair. Lone pair is kind of in the middle. But the big thing is the lone pairs pushing these 2 bonds closer together. So we use this theory to help us predict bond angles, maybe in unfamiliar molecules. So if you saw something like this and you drew the Lewis structure with the lone pairs, you'd be able to see, well, it's going to be this angular, or when I remember it, it was called bent, which is really unimaginative. But the idea is you've got two bonds and they're being pushed closer together. This is why I think in the beginning when we started drawing Lewis structures, and it's a common thing, you might have drawn this in a straight line, right, and the lone pair up top and a lone pair down below. Well, the reason why that doesn't happen is because that would be more repulsion, right? But the molecule here can minimize the repulsion by having this bonded pair, bonded pair, which is the least amount of repulsion. So it's how do you get all these different pairs of electrons around a central atom, and not all of the repulsion is even or equal. So the lone pair takes up more space, right, or more repulsion, pushes these closer together. So that's the best arrangement that would happen, as opposed to like if it was in a straight line, because you'd have bonded pair, lone pair, kind of operating here. All right. This one is a weird one because this is a metal, beryllium, and hydrogen is a metal, but there's exceptions to every rule. That's the rule of chemistry. This would be linear. This would be in a straight line. So you're going to have this kind of shape. I don't have a central atom that makes that same shape, but it'd be in a straight line. It'd be 180 degrees bond angle. 0 lone pairs, 2 kind of areas where there'd be more electrons, the 2 bonds right here, and that would be linear. So again, a weird example, but they do exist. All right. right, carbon dioxide using these ancient models looks like this. All right, we've got 0 lone pairs, we've got four bonds, 4 bonded pairs, but really just 2 areas where there's concentration of electrons or more density of electrons, and that's going to give us a linear shape. If this had lone pairs, it would start to bend in this way, but it doesn't. All right. pH3 is very similar to NH3. Let's just pretend we can use these interchangeably. 3 bonded pairs, 1 lone pair. Not as much repulsion as this one, right? Because you've got 2 lone pairs on this one, so the repulsion would be greater here. But to minimize it, you'd have a bonded pair next to each other. BH3, boron is in group 3, and it's a really weird example. But the story of boron here is that it makes this trigonal planar shape. It has 3 bonded pairs of electrons, 0 lone pairs, which is weird because that doesn't make an octet. And again, there's an exception to that octet rule, and this is it. So boron, if you imagine that this is just this bond here is the same as one of these, it would be 3. They're all in the same plane, so they'd all be kind of flat to the page. That's why it's called planar. Trigonal for 3, but doesn't make an octet, which is a bit of a weird example. But again, there's always exceptions, right? OF2 is like, if you imagine it like H2O, it's written a little differently. But if you imagine that these are fluorines here, 2 bonded pairs, 2 lone pairs, 4 total, and it's like an angular shape. Nitrogen makes a triple bond that looks like this. 3 bonded pairs, 1 lone pair, but really they're identical, so it's kind of the only shape that it could be will be linear, right? So this isn't the ultimate one rule for everything guide here. Sometimes you have to look at the arrangement. Make the model often helps to see the shapes. H2O we've kind of covered, similar versions of that. Here's a carbon. So even though the elements are all often make similar shapes in the same group, they don't always. One element doesn't always make tetrahedral or always make linear. Oh, excuse me. So just don't fall into that trap. So here we've got double bond here, and then 2 bonds here. So there's 0 lone pairs, but the 3 areas would be kind of making it trigonal planar, like all in the same plane. And then last, we've got this, weird example. I told you that the noble gases don't really make bonds, but very occasionally you can get them to do that. This one's got 8 bonded pairs, so it doesn't follow that octet rule. Some of the bigger elements kind of do something different. And we can't make it easily because of the limitations of the model. But there's 8 pairs of bonded electrons, 0 lone pairs, but the arrangement would be tetrahedral. So that's the idea of molecular geometry. The models really help. They're a little old school and beat up, but they do help you visualize it. Kind of the big takeaway is that you've got pairs of electrons around the central atom. They repel each other. They don't always repel evenly. Lone pair is the biggest, and then bonded pair is the least amount of repulsion. And they all make slightly different shapes. This would be your cheat sheet. Once it's complete, we can predict the shape based on these things using this prediction, like the VSEPR theory, but also making the model would get you there too. So that's molecular geometry. That's the idea of how electrons are arranged around a central atom, also how molecules have unique shapes. This will also come into play when we talk about the next thing in this unit, which is polarity, but we'll be using those models to kind of explain that too. Anyway, that's molecular geometry.